Good day, everyone. I welcome all of you to my channel, More Connect. Don't forget to subscribe to the channel so that you get amazing videos or tutorials on your subject physics, chemistry, biology, and then mathematics. Today, we are dealing with physics, where we are considering Doppler effect. Doppler effect is one of the basic topics in physics which every physics student or science student should have them on their fingertips. Okay. Now, by the end of this lesson, each and every student should be able to understand Doppler effect, as well as understanding the formula or the formula that will be used here. Everyone should be able to understand and then derive the formula. Yes, deriving the formula is a little bit challenging when it comes to applying them to solving questions. But we are going to deal with that very easily. Yes, so Doppler effect is a relative motion between sound and an observer. So here we are comparing two things, which is sound and an observer. Okay, it is relative because it depends on the observer. Now, if I have, so in the case where I have, in the case where I have observer, let's say I have observer A here, and then I have observer B here. If there is a sound or let's say a noise in the middle here, you realize that A might say that this sound is too low. Okay, A might say that this sound is too low. B might also say that this is too high. Okay, the sound from this area is too high. So it means that both A, as we see here, and then B here, they have different hearing capacity. Okay, so it is relative. It depends. So we have something we call loudness. Okay, a sensation that is created in the human ear. So it solely depends on the individual which is involved. Okay, so let's see. Yeah, so we're talking about the sound and an observer. Yes. Now, Doppler effect considers or take into consideration two things. Two things. The first being sound and its movement. Sound and its movement. And the second being observer and its movement. Now, we are dealing with two things in Doppler effect. Sound and an observer. Movement of sound and the movement of the observer. Now, let's get here. Okay, let's get here. Let's get over here. All right. So we have A here. So let's say the circled A here is an ambulance. Okay. So this is an ambulance here. And this ambulance moves from hospital to, let's say, another hospital. But A here. No, let me make it B or M rather M. So this ambulance stopped here. So it moved from a particular hospital, say hospital D, okay, to a particular hospital, say D. Yes, so a particular hospital, say D. So this ambulance was coming from this side. Oh, sorry. This ambulance is coming from this side, D, go to A and stopped. Now, M is an observer. So look at the distance here. M is an observer here. And then we have V being another observer. Now, if we look at what is going on here, the sound, the sound from the ambulance A, which is at a stationary point, is being heard. Is being heard. So it's being heard. So it's being heard by M here, okay, and it is being heard by V here. So if you look at that, we could see that the distance between A here and M is shorter as compared to the distance between A here and V here, where we have M and V being observers. Now, sound will travel more to M and then lesser to V because of the distance. Okay, so if V was also to be closer somewhere here, V would have heard more about the sound produced from A than M. So it means that distance or movement is also considered when we're dealing with Doppler effect. Even though we have the source standing, then we have the observers here, we can still have movement playing a role here. Okay, so we have cases where the ambulance would be moving. So if you consider the ambulance, okay, so if you consider the ambulance moving, okay, let me reduce it a little. It's too small. Okay, so let's say we have M here, and we have our V here, and then ambulance A is going in this direction. Okay, ambulance A is moving in this direction. Now, yes, we can still have M being closer because A will pass M. It will pass by M. So here we can have this A here go in this direction, but the sound will be heard at a higher peak at M before when it gets to V, it's also hear it at its peak. So movement is really important in Doppler effect. Okay, so let's consider the general formula, the general formula from, so let's consider the general formula from Doppler. Yes, so Doppler gave this formula out where we have F equals V plus or minus V naught over V plus or minus Vs. Okay, so here is supposed to be S. So multiplying F naught. Okay, so let's consider that here. Let's consider that one here. Yes. So we have, oh, sorry. Okay, so let's get back to the general formula. Let's get back to the general formula. So this is the general formula from Doppler, okay, where we have, so here supposed to be S, okay. So always the numerator here is the portion for the observer, and then denominator here is the portion for the source of sound, okay. So the F that you see here is the apparent frequency, or the frequency which is being heard, okay. So the frequency which is being heard by the observer. So in a case where an observer hears a sound from a far distance, or even at the same spot, some people might never hear the actual frequency produced from the sound, because we all have different hearing capacity. Okay, so we all have different hearing capacity. Yes, so we would have F here. Yes, so F here as the frequency the observer was able to hear in terms of the production of the sound. And this F naught here is the original frequency from the source of sound itself, the original frequency produced from the main source of the sound. Okay, the V that we see here is the velocity of sound in air, which is constant. So the V that we see there, the velocity of sound in air. Yeah, so let me bring the thing here to make it simple for you. So we have F, so F being equal to, so we have V plus or minus V naught, okay. So V naught divided by the same V plus or minus Vs, and all this multiplies F naught. So this F is the apparent frequency, okay. The frequency, this is not the frequency produced from the source or the sound itself. This is the frequency in the ear, okay. So I am saying in the ear because that is loudness, what the observer perceives to have heard from the source of sound. That is F, and this is F naught, the frequency from the main source, okay, of the sound. This is velocity of sound in air, this velocity of sound in air, which is constant, and that is 330 meter per second. Okay, 330 meter per second. And we have V naught is the velocity of the observer, and then Vs is the velocity of the source. Okay, so V naught is the velocity of the observer, and Vs is the velocity of the source. Yes, so that is why about the general formula. Okay, so let's look at situations to apply these laws or these formulas. So we have a situation, the initial situation, which is uh, okay. So we have the initial situation, which is a stationary observer and a stationary source. Okay, a stationary observer and a stationary source. Yes. So the first one, stationary observer, and a stationary source. Now, the moment something is stationary, it means that the thing is not moving. Okay, so if an object is not moving, then we have the velocity of that object to be zero. Note, there is no information that there is no sound produced. We only said there is a stationary source, not a no producing source of sound. Now, ideally, there should be an observer and there should be a sound in Doppler effect. But as to their movement, it depends on the question. Okay, so you don't have to be ideal about you having a no sound produced. No, no. No matter what the question will put, we will still have a sound. Just that the movement will determine the type of formula or the form of formula we would use. Okay, so let's look at the first one that we have. Now, we have a stationary observer and a stationary source. This means that the velocity of the observer and the velocity of the source is zero. So we can rewrite that formula as F is equal to, we have this here, the V is the velocity of sound air. No matter the situation, you will still have these two V's in the formula, where we have V and the long vowel count, another V. So let's get here. So our plus or minus is still there, but the observer is stationary. So the V naught becomes 0. And then the source is also stationary. That also becomes 0. And then we have our F naught. Now, if here is 0, here is 0, it means we can still have the formula in this form. Yeah, so we can still have the formula in this form. So we still have the formula in this form. So here becomes 0, here becomes 0, and here becomes 0. So they will all cancel out here. Now, we don't have anything here. So we still have to get rid of this. We'll get rid of all this here. And then we would be left with the velocity of sound air, velocity of sound air. But these two are constant, okay? So they can still cancel out. So when they cancel out, you have something like that, something like that. And you have F is equal to F F naught. So we have F is equal to F naught. So for every question that you have a stationary observer and a stationary source, the formula will be equal to F is equal to F naught. Okay, this is an ideal situation. Okay, yes. Now let's go back to the second situation, which is observer moving towards a stationary source. So let me clean what is here. Observer moving towards a stationary source. Observer moving towards a stationary source. Observer, we have observer moving. Let me finish cleaning and then we continue with the formula. Yes. So we still have our formula. F is equal to, then we have our big parentheses here. F V plus or minus V naught. This whole thing divided by V plus or minus V S. Okay. Then we have our F naught. Yes, and we have F naught here. Good. So we have observer moving towards a stationary source. Okay, so let's see. Now, let's consider this. Let's consider this. If I have a source of sound, so that we are still using the ambulance here. A, let's use the ambulance as our source. This is stationary. Yes, so this is stationary. Okay, the ambulance is stationary. And then I have an observer moving towards an observer going to direction, moving towards the sound. Now, as the observer moves, okay, so the observer starts from a particular distance. As the observer moves towards this stationary sound, you have an increase in the intensity of the sound because as you move closer to a noise, the more you hear it. So that means if the observer starts walking towards the sound, the frequency it will hear will be more. That means this frequency here is increased. Okay, so it starts increasing the moment this moves towards the source. So what I am saying is that the F here will start increasing because this is moving towards, this is stationary, this is moving towards it. Okay, now this is stationary, so it means that the velocity, I told you that this v here and this v, they are constant, so we just work on these two to get your plus or minus. Okay, so this is stationary, so it means that in the formula here we can deal with this to be 0. So if this is 0, then we can have the formula in terms of the denominator as this, because it is 0. Since it is 0, plus or minus 0 is still 0. So we can take this out. And then we will still have our V here, not Vs, because Vs is 0. Now, this is moving towards it, but it hears the frequency increasing, okay, at a higher rate as it moves towards it. So this here becomes a plus because to get a higher value of f, the numerator should increase. So let me take you through a simple mathematics here. If I have 4 over 2, so we say 4 divided by 2, I have my answer to be 2. Okay, then if I have 10 over 2, okay, let me clean this. Then if I have 10 onto, I have 5. So the earlier one I had 2, this I had 5. So it means before I will get a bigger value for f, the numerator should increase. And here, increasing numerator involves plus, because I started with 4 on 2, I added 6 to the 4, 10 on 2, because the v is constant. This is just a technique for you to derive the formula rather than doing chew and pour. Okay, chew and pour will never help you. So we have to increase this in terms of getting a higher final answer as 5, which is the f. So ideally, moving towards this stationary sound and getting a higher f involves here being plus. The velocity of sound is in the air already, and the velocity and the observer is also moving. So it means that this can never be 0. So we would have our formula to be we will have a plus sign here, okay, and then we still have what is here, v naught. So we use this to solve for any question on Doppler effect, where we have a stationary observer, but the sorry, where we have a stationary sound, and then the observer moves towards the sound. Yes, so this is more Connect. Subscribe to the channel and then wait for the second part of this nice lesson. You would never miss a day of not teaching you. Okay, so subscribe to the channel and let's read more. Thank you.